Slide 1. Good morning, ladies and gentlemen. My name is Bernard Lucien Ling, and the title of my presentation is The Promise of Cellular Automata as a Class of Models for Urban Tourism. Slide 2. This presentation focuses on 6 main areas that I think will be relevant to urban tourism modeling. As this is the first time some in the audience are encountering the notion of a cellular automata, I have included visuals wherever relevant. The outline of the presentation is as follows. To start off, I begin with a brief history of cellular automata as a class of models and as an integrated simulation environment, followed by a description and explanation of the various elements of a cellular automata. Simulations as a third way to do science is also discussed, especially in its relation to the economic science. This lays conceptual and methodological foundations upon which to advance the application of cellular automata in urban tourism research. Finally, I discuss the promise that cellular automata holds for the modeling of urban tourism, both in the sense of future research directions and variations on existing implementations and applications of cellular automata. Slide 3. The figure shows two one-dimension cellular automata that has evolved through 250 iterations, where the vertical axis denotes simulation steps and the horizontal axis denotes the size of the simulated data measured in cells. Slide 4. The diagram shows the possibilities space of the dimensions of a cellular automata model. 1, 2 and 3 dimensions. The typical neighborhood setup for cells and the transition rules of individual cells depicted graphically. Evolutionary trajectory of each cell is also outlined as a branching process. Slide 5. The lattice of a cellular automata can be finite or infinite. The lattice space defines the simulation possibilities of a cellular automaton, singular. A finite cellular automata will stop once the emergent patterns reaches the boundaries of the lattice, while an infinite lattice is implemented by allowing the patterns to fold back onto itself, infinite boundary setups. Further modifications to the lattice can be achieved through changes in the size of the lattice, shape of the individual cells in the lattice, and by specifying the dimension of the lattice as a whole. 1, 2, or 3 dimensions are quite common. The states of the cells of a cellular automata denotes the values of the simulated data. Often each cell is viewed as an independent agent, hence automata or automaton. Every cell is updated in parallel in each iteration, and the end state of a cell depends on how it processes information around it. This is defined by the neighborhood setup of the cells and the transition rules of the cells. Slide 6. The history of scientific progress has been marked by milestones in the development of models and archetypes. The history cellular automata parallels the evolution of computation as a science. Cellular automata owe their existence to the genius of early computational theorists such as Ulam and von Neumann in the 1940s, 50s and 60s. Since cellular automata operate on recursive rules and result in patterns that are akin to fractal geometry, cellular automata have been utilized in the morphological study of snowflakes and urban networks, Batty 2005. Slide 7. I am particularly interested in cellular automata as a modeling environment because it is amenable to modeling economic processes at 3 order levels: the micro, the meso and the macro. Conventional economics uses comparative statics that unravels the micro-macro connection. Yet it is at the meso level where the transformative processes are often veiled in mystery and are at best relegated to a black box in the model building process. Peeking into such a black box is possible with cellular automata, since every cell in a cellular automata is updated in parallel upon every iteration, and every unfolding event is captured by the simulation model both visually and numerically. While this might not provide the complete picture of the causal mechanism underlying a phenomenon, it does provide a detailed snapshots of the elusive parts of the complete causal mechanism. Thomas Schelling is one economist who has advanced this idea of a meso-bridge through his segregation model, though he did not explicitly call it a cellular automata. The title of his book Micromotives Macrobehavior seems to point to what is lacking in economic methodology. Thankfully, a theoretical and rule-based foundation for evolutionary economics that is rooted in the micro-meso-macro progression has been developed by Dopfer and Potts in their 2008 book entitled The General Theory of Economic Evolution, which builds upon knowledge-centric foundations laid by the Austrian school, most notably, Hayek's 1945 book, The use of knowledge in society. Slide 8. Henceforth in the presentation are points on the promise of cellular automata in modeling urban tourism phenomenon. Both the inductive and deductive elements of thinking in the scientific method are incorporated in cellular automata. Rules hold the key to understanding the meso level. For rules embody in them insights about the transformative process. Cellular automata rules are formulated based on induction, or they may originate from an axiomatic system. Empirical findings and stylized facts are tested and simulated through the deductive approach, where recursive operation of these rules leads to macrostructures being grown from the micro-level seeds, cells. Cellular automata embody a philosophy of science where clinical perfection in the quest for knowledge and insights do not jeopardize the trial and error, adaptive search needed in uncovering causal mechanisms. Slide 9. Cellular automata allow us to overcome the problems of dimensionality that plagues so many analytical efforts, mainly manifesting itself in mathematical intractability. So that progress need not be stopped dead in its tracks at the prescient stage of problem formalization. Slide 10. Simulations have very close ties with the experimental thrust in science and economics. This is the first part of a quote from the eminent experimental economist, Vernon Smith, in which he contrasts conventional economic methodology rooted in econometrics with that of experimental economic methodology. I should add that cellular automata simulations are not a substitute but a complement to conventional economic methodology. While an econometrician adjusts models to fit field data, what is termed model fitting, Vernon Smith goes so far as to refer to a fitting of a researcher's belief system. Cellular automata researchers attempt to see what happens to data when the model is tweaked. Slide 11. Going with the spirit of this second part of Vernon Smith's quote, I suggest that cellular automata simulations assist in scenario building, allowing the conventional economist to narrow down which is more likely to be the candidate scenario to glean data from, and thereby to fit models and estimation methods. So that even though economists do not have the leisure of performing experiments, they are readied for one when the opportunity arises. Some may object to this view and remind us that cellular automata give credence to the age-old accusation that economics methodology is flawed because of the unrealistic assumptions on which its models are based. While I don't completely dismiss this accusation, all I would say in defense of economics is that perhaps its methodology has not been efficient enough in identifying the candidate scenario, what scientists would call the crucial experiment. Think for instance about Darwin's Galapagos Islands, which for him was an impetus for all kinds of thought experiments, from which to extract data that will allow it to corroborate the assumptions of its models. The argument for the use of cellular automata in economics still stands despite Roman Friedman's, not to be confused with Milton Friedman, critique that all economic models will fail someday due to imperfect knowledge and reflexivity. In which cellular automata. My point in advancing the use of cellular automata is that you need a compass to tell you which model to cling to and which ones to abandon. And when you wait for the real world to invalidate your model, it would be too late. The problem is not that models are deficient. The problem is that some economists are so enamored with their models that they would rather tweak and window dress them by going through some econometric somersault than abandon them when the situation so dictates. Slide 12. There is a sense of seamless change in so enamored of their cherished models, since the use of recursive rules allows emergent patterns to be reduced to basic axioms, and conversely for these axioms to be scaled up through the three economic orders. A higher degree of completeness is achieved by treating constellation of cells as institutions and the agents of change. Once fuzzy notions such as catalepsy and concatenations, the twin perplexing notions in Hayek's treatment of knowledge in society, comes within closer grasp of the researcher, modeler. In the use of cellular automata as modeling environments, there is a blurring of the distinction between analytical and operational models. In fact, being a discrete event simulation, it is the embodiment of both. Offering a third way to do science, Axelrod 1997. Therefore cellular automata allows for the breaching of the endogenous-exogenous membrane, providing a complete, consistent and integrated simulation environment. Slide 13. While Albert Einstein has been famous for advocating simplicity and parsimony in model and theory construction, he is also famous for emphasizing that problems can only be solved from a level of consciousness which is higher than the one that originated them. leading some to conclude that good models are at least as complex as the phenomenon they describe. Cellular automata and complexity science has shown that the parsimony criterion can be satisfied since complexity may be produced by simple mechanisms. Partly because with feedback loops, emergent patterns may exhibit complexity that is many degrees higher than their underlying rules. To this extent, Einstein's observation that problem-solving require higher consciousness is partly true if we take a top-down approach. Cellular automata suggest an alternative approach in which is bottom-up, and is a generative approach to problem-solving. Slide 14. Because tourism phenomena are largely discrete, a molecular and discrete model such as cellular automata is less susceptible to attack on the grounds of representativeness. In fact, it may very well be possible for tourism phenomenon to be computed just as some have argued that our physical world is computable. Wolfram, 2002, has advanced the idea that due to the principle of computational equivalence, the use of cellular automata offer a new way of doing science. In fact, the foregoing slide has hinted to this, where we have highlighted the dilemma of a top-down approach to problem-solving/science. Slide 15. While rule specification and phenomenology cellular automata mappings help to formalize our insights into tourism phenomena, the real strength of cellular automata lie in their massively parallel information processing. Each cell in the lattice is an independent computer processor, which means that a group of cells may constitute a swarm computer. Cellular automata dynamics allow us to understand spontaneous order, and how seemingly chaotic, uncoordinated individual actions can give rise to order. From a top-down, structural perspective, this also suggests to us that parallelism is a vital key in unlocking the power of complex adaptive systems and urban destinations. Slide 16. Henceforth the discussion will be focused on the application of cellular automata to urban tourism. The life cycle figure depicts the scope of processes that may be modeled in connection to a destination's evolution. The modeling possibilities of cellular automata are associated to tourism development, initialization stage, tourism management, growth maturity stage, and tourism innovation, decline stage. Slide 17. Taking cues from the new economic geography, for example Fujita, Krugman and Venables 1999, there are a number of tourism development issues that can be investigated through cellular automata models. Cellular automata can be used to provide a sense of the range of possibilities associated with certain policy levers. This harks back to Goethe's idea of morphology as the science of the possible. Perhaps another way to think of cellular automata in terms of the embodiment of Goethe's philosophy is to treat cellular automata as machines for argumentum ad infinitum. The fallacy of argumentum ad infinitum is then circumvented by interrogating the persisting arguments, or other patterns, with the criterion of resilience. A notion I shall elaborate further towards the end in slide 21. Cellular automata also allow us to trace the evolutionary paths or growth trajectories of destinations. For economists are not just interested in equilibria but the routes taken to reach them. Destination systems may be classified according to their key salient features. The visualization of cellular automata are a great help in this endeavor. Again, this is taken up further in slide 21. While system stability in the form of equilibria may be the primary focus in most interpretations and use of economic models, cellular automata may highlight invariant structures in a cross-section of destination or intertemporally within the same destination. A structural interpretation of tourism systems is possible when visualizations of cellular automata are interpreted as conurbations, especially when these can be mapped to certain stylized facts derived from economic geography. Slide 18. The growth and maturity phase of a destination often coincide with convergences and transitions. Follow the link on the screen. Based on this premise, it is important that in tourism management a consideration is given to the range and continuum of change within a destination system. In particular, where and when does it give rise to the edge of chaos? Langton 1990. In the consideration of range, continuums and transformations, the focus of the modeling efforts will be on cycles, life cycles, thresholds, shifts and transitions. Issues that are of particular importance in the meso-level of a system. Unlike micro-level issues that should rightly be the preoccupation during the destination development phase. Slide 19. Henceforth in the discussion are the modeling possibilities relevant to tourism innovation. The degree of tourism innovation may be treated as a special instance of innovation in general which can be diffused spatially. Hager Strand 1952. Spatial patterns have two sides to them. An objective element in the more traditional sense of spatial autocorrelation and a subjective element that requires an interpretation of the states or spaces, or places. Taken together, objective and subjective elements of destination patterns combine to give a spatial economic characterization of urban tourism. The objective elements of the spatial structure allow us to infer multiplier and agglomeration effects. Multiplier and agglomeration effects are in turn correlated with the degree of hierarchy, centrality, centripetal and centrifugal forces, and the existence of power law distributions. Telltale spatial patterns are clusterings and the formation of network structures in cellular automata simulated patterns. Slide 20. The color of cells in a cellular automata can be mapped to certain states of the phenomenon studied, giving us a qualitative assessment of the destination as a whole or that of subsystems within a destination. Together the colors of cells and their density in space completes the spatial economic characterization of a locale. Different policies embodied in cellular automata rules can be evolved over a number of iterations as a kind of experiment to discover which has the targeted effects. More broadly, each experiments can in turn be interpreted as different possible scenarios arising from policy implementations. Literally the use of knowledge in society, destinations. Slide 21. Complexity science informs us that certain types of system are more likely to be resilient. There is therefore a connection between complexity and resilience. In particular those classified as complex adaptive. Wolfram, 1984. Has attempted a typology and classification of one-dimension cellular automata, resulting in 4 types of systems. In general, destination systems can be classified under one of these archetypes. Cook, 2004, has shown that some one-dimensional cellular automata based on Rule 110 in Wolfram's classification scheme are capable of universal computation. Restated for our urban tourism context, some destinations may be super-resilient. Rule still unknown, because they are robust enough to handle all possible eventualities and to thrive in them. Slide 22. The future of cellular automata-based investigations in tourism may involve non-standard features of cellular automata such as asymmetric grid sizes and asynchronicity in cell updates. Changes to the lattice boundaries and transition rules resulting in patterns that are stochastic. And instead of cells, one may choose to use nodes and vertex to weave graph cellular automata. Moving on into the future, cellular automata as an idealization of urban tourism processes may be combined with empirical data in the form of remotely sensed, geotagged images, mediated by GIS applications, resulting in some kind of tourism expert systems. I also foresee augmented reality applications to tourism being informed by heuristics which is derived from real-time cellular automata simulations. Slide 23. In the end it could be said that cellular automata help us to build microcosms of urban tourism phenomena. Together with the cellular automata visuals, much of the slides contain artwork by M.C. Escher, who has captured perfectly William Blake's take on the world around us. Thank you all for your time and attention.